Just by the way, there is a famous complication to this theorem that was analysed by Einstein in 1905. We shan't go there now, but we'll provide a link if you want to see where that very famous equation comes from and why it is consistent with our definition if v is very much less than the speed of light. You may be wondering, why does kinetic energy go as v squared? Where does the squared come from? The answer is kinematics, but to see that directly, let's look at the quantities as functions of time. Suppose that we start with an object at rest. We supply a constant force for a certain time t. Next, we apply the force for twice as long. Constant acceleration for twice as long, so it ends up with twice the velocity. But how far does it go? For constant acceleration from rest, the distance travelled goes as t squared. So for a time twice as long, we apply the force over 4 times the distance. It takes 4 times as much work to double the speed. Here's an important example with application to road safety. I apply a constant braking force to stop my bike. 180 degrees between braking force and displacement of the bike, work done by the brakes is negative, so kinetic energy decreases to 0. If I'm travelling twice as fast, I have 4 times as much kinetic energy, so the same braking force needs 4 times the distance to stop me. Please remember that on the road. Remember what we've just done. In one dimension, work equals total force times the distance. But for constant acceleration, our kinematics equation 3 said 2a times distance travelled equals v squared minus v0 squared. Substituting that gives work equals change in a half mv squared. So we define half mv squared to be the kinetic energy, and now we can say work done by all forces acting on the object equals increase in its kinetic energy. What we've proved is a theorem. It's just a mathematical manipulation. It's not a new law. We defined work. We then substituted from Newton's second law, F equals ma. We used an equation from kinematics. Finally, we defined kinetic energy. The only physical law we used was F total equals ma. So the work-energy theorem is logically equivalent to Newton's second law. If one is true, so is the other. Falsify one and you falsify both. Nevertheless, the idea of energy is a powerful concept, pun intended, and it gives us a very different way of looking at the world. It's often helpful in doing problems, and that must be a segue into a quiz.